Every time it gets bad, just remember the weekend's coming, even if it's Monday. I think yeah, we worse.
Good evening, everybody. Welcome to Advanced Refrigeration Podcast. You're here with your host, Brett Wetzel, Kevin Compass. What's going on this week, Kev?
Oh, bouncing around and doing some did some condenser change outs this morning, and for the last 4 hours I've been working on my personal vehicle, and I never want to be a I I hate dealerships, and yeah,
That
it's
sounds
just
fun.
it's a bad time when my wife walks out in the garage and she sees a tap and die set and a welder sitting right next to the truck, and I'm just throwing things.
She's like, I'm stepping away.
Yeah, she
Well, yeah.
walked back in the house.
See, I've heard, just recently I heard that you do get angry and you throw shit sometimes. You throw shit in the motor rooms.
Yeah, well, sometimes it happens.
You'll have that on on those big jobs.
Don't act like you never threw anything.
Honest to God, I've never have.
Like, dude, you just threw that filter across the room. Now it's disintegrated. Oh man.
No, no, I've yelled in just complete, just as loud as I can. The one time I did, because I couldn't find this fucking short, and the store manager comes up. He's like, "Are you okay? We thought you got electrocuted or something. Something happened." I was like, "No, no, I'm just hating life right now. I've never thrown a tool or refrigerant cylinder in anger."
You
So
should give it a try. It's a major stress reliever. The holes in the back of my garage door from wrenches skipping across the garage.
where'd that 10 millimeter go? It probably went 3/4 of the way through that half-inch drywall. Well, tonight we got Joe Sigg from Coolsys Energy Design. He's going to be walking us through how to size different components on CO2 rack, going from shit. We'll do compressors and flash tank and lines and valves. Oh my, we'll do it all, right? You go with that,
Absolutely.
Joe?
Yeah. Yeah, absolutely. Yeah.
So
Hi, I'm Joe Sigg. I work for Coolsys Energy Design. We're part of the professional services branch of Coolsys, which is based out of Brea, California. They're a nationwide, here's my plug. They're a nationwide contracting company. They perform refrigeration, HVAC, electrical, and plumbing services for a variety of different end users at this point, and they're always looking for more. Anyway, I'm the refrigeration department head over at Coolsys Energy Design. I'm directly involved with all the refrigeration work that comes in our door from an engineering, commissioning, construction administration standpoint. I deal with it all. So, yeah, I'm here today to talk about the mystery of CO2 systems and how they're put together from a sizing standpoint.
go ahead, Joe.
Okay. Yeah. So when you're putting together a CO2 design for a client from an engineering standpoint, there really isn't a lot of difference from a DX system design standpoint to when I'm talking DX, I'm talking synthetic refrigerants such as R4, R22, R44A, R448A, R449A, R47A, so on and so forth. Those types of system designs are not that far off from CO2. There is certain things that you need to worry about or think about when you're doing the design for a CO2 system. And the one big thing that I'll just get into at a high level right now, when you're sizing a CO2 system, the first thing you need to do is you need to critically analyze where the location is that you want to put this system in. If you're talking south of the Mason-Dixon line, you really need to think about temperatures of climates and how hot it's going to be in the summer months of that area. Two has a critical point of about 86 degrees. And once you get over that critical point, the system will go into what's called transcritical mode. And the gas now becomes a multi-phase mixture, basically. And it's not a liquid, it's not a solid, it's not a gas. You don't know what it is and what percentage of what constituent it is at that point. So what that does is when you're operating above 86 degrees head pressure, you actually start to cost a lot more money and energy spend from the system running, because the system has to work a lot harder to maintain that refrigeration effect in those connected fixtures, things of that nature. So when we size our systems, we'll use different technologies to overcome those hotter ambient conditions. For example, we just finished a refrigerated warehouse in Houston, Texas, which is the armpit of the nation. It's humid, hot, it's nasty. It's just a bad area for ASHRAE conditions.
Smells bad. Smells
No,
bad.
I'm not even getting into that because that doesn't affect refrigeration version. But yeah, but I mean, like, so what we did there was we opted to go for parallel compression, and we actually introduced ejector technology into that design, which we're working with a partner, an OEM partner, to put that into the system design for for that location. And really, when it comes down to it, you with CO2 systems, you need to worry a lot more about how much spare capacity you have on your compressors, your gas coolers. You need to look at your line sets critically because when you go from DX to CO2, your line sets can get a lot smaller because CO2 has a lot more BTUs per pound than conventional DX refrigerants. You're going to get about a 3-to-1 ratio of BTUs per pound from CO2 to a DX, any DX refrigerant.
And you don't really get much subcooling out like in the flash tank, right? I mean, for the most part, it's usually maybe what 1 to 2 degrees of subcooling. So wouldn't you run the risk of ending up getting flash gas easier in the liquid line because there's that little of subcooling, and that's one of the reasons besides having a low saturated condensing temperature, but also insulating that line to prevent it from flashing because of that low subcooling, correct?
Well, so the reason that we insulate the liquid lines on a CO2 system is because the liquid coming off due to the hot gas bypass valve that's coming off of the flash tank, that's set to maintain roughly whatever it's this preset temperature, but it'll maintain a certain temperature in that tank by relieving the gas off the top of the tank. Typically, what we size to is we size the 38-degree liquid. Then we don't have to include the mechanical subcooler.
Mhm.
And we just do that by utilizing the hot gas bypass valve and in conjunction with the head pressure valve.
You're referring to the bypass gas valve, the line that goes from the flash tank to the medium temp suction.
Correct.
Okay, just in case someone's like, "Well, what's hot gas line? What's he talking about?" I just want to make sure that we're
So
on the same page.
yeah, so that hot gas bypass valve, it is mounted. There's a port that comes off of the side of the flash tank, and it's mounted up pretty high so that it can catch the gas and not the liquid. And then that valve is a modulating valve that basically will modulate open and close to maintain a pressure inside that tank by bleeding off the gas to the medium temp compressors, the suction of the medium temp compressors. So again, when we insulate the low temp or the CO2 liquid lines, whether they're low or medium temp, we're insulating them all typically. And the reason for that is we're getting the low temperature, or should I say, quote unquote, subcooled liquid temperatures going out to the fixtures.
Okay.
So, another little intricacy of a CO2 system is that you don't technically need mechanical subcooling if you program the system and set it up right from how you're running it. So, for example, the Hill Phoenix system, the Advancer system, automatically includes all those valves in its standard design. So, as long as it's commissioned and set up properly, you don't need to worry about any kind of subcooling whatsoever because you're going to get it off of the flash tank.
Gotcha.
Yep.
Okay, and usually the reason why your load is so important is because not only do you have the load of the refrigeration for those medium temp compressors coming off of those cases, right? You
Mhm.
also have the load from the actual low temp compressors discharging into there, right? You
Correct.
also have your potentially hot gas bypass for either load control or low superheat control, right? Potentially have liquid injection, and on top of all those things, your gas to liquid ratio versus when you're in transcritical versus subcritical. Like, so if you're running subcritical, from my understanding, it's usually about 50% liquid being created, and I'm sorry, 70% liquid being created and 30% vapor. And then when you run that transcritical mode, that it decreases because now your gas cooler is just that, it's just superheating. So now you have about a 50-50 mix versus liquid versus vapor creation. And you'll see more compressors run when you're transcritical because of that, correct?
Correct, exactly. And
Okay.
what we'll see actually when you go into transcritical mode is you'll see that flash tank level drop because you're getting a mixed phase coming back rather than a full column of liquid. Your condenser, quote unquote, which is condensing the gas into a liquid at subcritical conditions, is now a gas cooler, which is only cooling the gas down as much as it can with the ambient conditions.
Mhm.
Yep. When we're sizing compressors for a CO2 system and gas coolers, we need to make sure we have enough spare capacity to overcome those transcritical conditions. When the system is operating inefficiently, when the system is operating not at its peak. Typically on medium temp and low temp, doesn't matter which group, which type of load group you're talking about. We're looking at somewhere from in the neighborhood of 15-20% spare capacity on our compressors. That's what we're looking
Mm, okay.
on standard BX systems. You're looking for anywhere from 10 to 12%. So we bump up that spare capacity because we know that when it gets to be 100 degrees outside, those compressors are going to have to work extra hard to make that system keep on operating the way it's supposed to.
So if you were to size it for the load of the cases, right? The
Yep.
medium temp compressors I'm talking about, if you'd size it for the load of the cases, and then you would size it for the load of the compressors going into it, and then basically whatever that would end up being, you would add 20% for that transcritical operation, correct?
Correct. Exactly.
That's a rough guesstimate, right? Like that's
Yeah.
yeah.
You're in the neighborhood. Yeah.
Okay.
Yeah.
All right.
That's an educated guesstimate.
It's a what? Educated guesstimate? Yeah.
Yeah. See, rough estimate where your engineering things.
So I'll take an example of a project that I just designed. I had on my low temp group, I had on my medium temp group of the CO2 system, we were condensing at 87 degrees, which is actually in the transcritical range because you're above 86. We sized our compressors. We had a total load on that group of 616 and a half MBH. We ended up sizing the compressors for 789.5%, or zero point 0.5 MVH. And that gave us 28.05% spare capacity. And that helped when you're in the medium temp side of life, you need to consider that you need that medium temp in order to run the low temp. So if your medium temp fails, your low temp fails too. That's a critically important thing that everybody needs to consider when you're putting in a transcritical CO2 system. So let's see. So what I can do is I can kind of share. Let me share some stuff here.
Let's do it.
Screen.
So while Joe's doing that, Kev, today I was making some training up, and someone told me they wanted a training for a certain customer, and they're like, "Yeah, it's liquid pump overfeed," and I basically got the liquid pump overfeed stuff doing. Like I started making the program and stuff, and then I get an email with the program, and I'm reading through the program like, wait a minute, this is like all the things that are usually in there, like the pump, all the pump stuff and the vessel, everything. It was typically for a liquid overfeed system. And then all of a sudden I started seeing some like cascade stuff. Like it had a high pressure of like 480. I'm like, what the hell's going on here? So I emailed them like, can you guys send me like some pictures? And here it's one of those systems that it's a liquid pump overfeed, but it's also a cascade all in one.
Yeah,
Have
we
you
have
ever
a,
seen-
we have a couple out here.
yeah.
They still working.
Well, I guess we'll find out.
You get all the problems of the liquid pumped overfeed, like the condensation issues, the insulation issues, the massive amount of CO2 it needs.
Yep.
Hmm.
All right. What
All
are
right,
we looking at, Joe?
So this is a project that we just finished, and basically what I have open is I have my schedule open, just kind of show the loads that are connected to the system,
Mhm.
the compressors that we chose, and then just some selling features of the system. Showing at the over on the other side here, we show the gas coolers that we selected,
Mhm.
and we actually used these super heaters on this project. A separate gas cooler that basically these super heats for low temp gas prior to putting it into the medium temp grid.
Yeah,
Oh, get you.
it's such a tricky line to walk, especially like out by us. Like they could quickly turn into the compressor murderer 5000.
Yeah, what ends up happening, Joe, if the line gets too cold where it actually starts condensing in there, those heat exchangers do not like that at all.
Really?
Yeah, and then like if they get liquid that's created from the desuperheater, because we've had it just here in
Oh,
Texas, and
Brett, these are like actual transcritical. What they're doing is they're running the low temp up through a loop of the gas cooler, and they use it to desuperheat, and then they dump it back in the medium temp, so that way it doesn't put as much load and hot gas into the medium temp.
oh, but then if it does condense, that means those medium temp compressors are just gonna get a slug of liquid.
Pretty much. We did a couple Costco's with that with zero.
Oh.
They had the valve set wrong the one time, and it was like 10 degrees outside. With as soon as the three-way valve opened up,
But you start hearing the compressors going.
they sounded like a 1986 Honda Accord.
Then hasn't been taken care of.
It felt Well, just this squeal of death.
Yeah. All right. So what are we looking at?
So what we're looking at here, this facility it's a large seafood freezer operation, basically. They were what the scope of work was here is they had to they have an existing facility, about 50,000 square feet. They're looking to put another 100,000 square feet beside it and expand the facility.
Mm-hmm.
So basically what we were tasked with doing was right now they have all rooftop condensing units, standard BX refrigerant serving evaporators in the space.
Mm-hmm.
They wanted to get rid of all that and go to a centralized CO2 system design. So we split the load up, the new loads and the existing loads. We did the whole thing. We put the loads on two separate systems. We have compressor rack A and compressor rack B here. And the reason we did that was just for redundancy. If one rack goes down or has to go down for service, they can keep half the facility up and running. We interlace the evaporators in the spaces so that they can keep temperature in the spaces while they're working on one of the systems. And that's one important thing to consider because it's more important with a CO2 system than it is with a DX system when you're talking about redundancy and large walk-in spaces like this. Because, like I said, if you take down the medium temp, you're taking down the low temp as well.
So I have a question because like everybody has a different flash tank pressure that they hold. Like I see yours saying 38 degrees, right?
Yep.
I'd have to get a PT chart out. I'm assuming it's going to be close to probably 520 or something like that.
Here,
Anyway,
I can bring that up right now. Just here with me.
all right.
It's like exactly what it is.
So my question is, why do some people do, that 38 degrees and then you see some RS schedules that say 33 degrees? So what is the benefit or why the difference in flash tank pressure?
It doesn't, there is no rhyme or reason. There is no standard. Anywhere in the 30s is good. Some manufacturers prefer 33, some prefer 35. We've standardized on 38 because it gets up near that nice 40-degree mark where you're not subcooling. You're not sending wild subcooled liquid out. It's just minorly subcooled.
Okay. All right.
Standard BX system. So
I would rather see it that high because then you avoid the oil issues. You avoid flash off issues with the valve sizing, like running the higher, and it's more efficient.
True.
You have,
because your BGV is not opening up nearly as much.
Yeah, you flash gas load.
So as you guys can see here, I put in 38. The pressure's 536. That's what you're looking at. Yep.
Okay.
So yeah, basically we went with Gutner because they're really good with industrial evaporators.
Yeah.
We like them a lot because they're single circuit. They're all stainless steel. They come factory installed with the Danfoss CCMT valves, which is really nice. Which is CCMT is the industrial brother of the AKV valve, the Danfoss AKV, which is the pulse EV basically. That's used.
So all the piping on this facility is it regular standard copper? Is it HXP? Is it stainless?
We went with all stainless last job.
Dang.
Oh, that's what the client wanted.
Do they orbital weld it or they do it by hand?
And they're doing all welding, all welded copper. Yeah.
No, I mean, like, are they using the orbital welding machine or are they actually TIG welding by hand?
Oh, no, they're doing it all by hand. Yeah. Yeah.
Oh, wow.
Yeah. The long arduous process, but that's what they wanted. So, and they wanted to make sure that they wanted them to do it by hand because they want to be able to monitor the process. The owner wanted to monitor the process and make sure that they're doing what they're supposed to.
Damn.
Yeah. And this owner is not a quote unquote dummy. I mean, he knows what he's dealing with here.
Yeah. The from TIG welding, if they don't flow argon through there, like the amount of like soot and like they call it sugar dust.
Yep.
There is like 10 times worse than burning pipe copper without purging.
Damn.
It's like this thick yellow soot.
It comes from the slag from the TIG, right?
Yeah, it's from the in the air from the actual process of the argon when it's the TIG torch is using it in the air on the inside, it like causes it to just condense and make that slag.
Oh wow, that's crazy. So what you can see here, I'm just going to show you guys my plans real quick. You can see we have these two large refrigeration enclosures. So they're actually walk-in houses with the gas coolers and the superheaters mounted over there.
Are those a Batic or are they dry cooler?
These are Gunther adiabatic condensers, adiabatic gas.
Those are freaking huge. What's that? 2, 4, 6, 8,
The
10.
16 fan.
Damn.
Yeah, they make them that big. They do.
Well, that's huge.
You don't see, I mean, you got, unless you work on industrial stuff all the time, you're not going to see equipment this big, right?
Mhm.
Like if you're working in supermarkets, you're not going to see a 2x3, 2x4.
Mhm.
You know?
It's been a minute.
Yeah.
Racks, or did you guys sub that out to like one of the OEMs?
So we subbed it out to an OEM. We worked closely with them on the design side of things. We actually we picked an OEM. The owner agreed. We went with the OEM and we made them comply with our design requirements. And that's the one thing that we do at Coolsys Energy Design that not a lot of other engineers I see do. A lot of times when you're working with an OEM, you get what you get because that's what they strong on. You know what I mean? They say, this is what we got and this is what you're getting. Well, no, I'm not willing to listen to that when it comes to me, because if I'm talking about a design, I'm already 3 weeks into it when I'm talking to you. Like, so basically what we did was we brought it, as you can see here, here's our pipe sizes kind of shown here. You got 4-inch horizontal suction, 3-inch liquid, 2-inch hot gas, supply return.
Oh my God.
Yeah,
4-inch liquid. That's a lot of BTUs.
we got a lot of BTUs in this facility. I mean,
Shit.
this is just one side of it. Here's the other side. This is the new addition. Head-house evaporator.
That's a lot of stainless steel. Oh, are those the out, like the one that has the owl on it? How's that called? Wise. Are those Wise ones?
Wise? What do you mean?
No, the manufacturer, the penthouse evaporators.
I don't know. The penthouses are getting stick built by the IMP by the IMP manufacturer,
Okay. Oh, and they're just Guteners.
and they're just doing their coils. And they're no, it's just a bare coil basically.
Okay. No, because like
Fan motors on the one side, and what we do is we're ducting it down and then shooting it out 45 degrees.
the reason why I was asking is because like when I did industrial, they had these Wise penthouse for like chocolate storage, you know what I mean,
Yeah.
for shipping. And it's just literally a penthouse that just gets sat on there, and then just the ammonia piping just gets hooked up to the outside. Like we all came in like one big container. It wasn't stick built up.
So you picked it up and set it on the roof and then break it up
Yes.
when you're done?
Yeah. It's insulated and shit, kind of like what this
Yeah.
is looking like, but it just comes as one package, just sets right on the roof.
Wow, that's pretty cool. I mean, I'm getting ready to start up another project
Mhm.
where we're going to be doing interstitial space penthouses above a freezer, a new freezer.
Mhm.
So yeah, we'll have to talk about that offline.
Yeah, for sure.
So anyway, this is the new freezer expansion. 4 penthouses, 8 evaporators total, large industrial evaporators, centrally located throughout the space to even throw even airflow across the space.
Yeah.
We're using, we chose to go with some EEVs for control with case controllers. We went with the Danfoss system because they're pretty much the leader when it comes to CO2 system control. I challenge someone to tell me differently.
The Canadians would disagree up north.
Oh yeah, microthermic.
Oh yeah.
Yeah, I know. As you can see here, we're showing all our sensors for defrost termination, the EV, return temperature, supply temperature, pressure, so on and so forth. All things you need: hot gas solenoid valve, liquid solenoid valve. All this stuff.
Who's the EMS guy? What manufacturer you using?
Danfoss.
Oh, okay.
Yeah, here I'll show you our one line. So you can see it here. There you go, Danfoss AKs SM880.
Well, that's what I was getting at. I was wondering what case controllers you were using to operate. I didn't know if you went like I don't know if like Opto 22 has case controllers and shit. That's why I was asking.
Yeah, so we went with the CC550,
Mhm.
which is the individual case controller, can only control one valve to one
Mhm.
coil. Danfoss had, keyword being had, the AKCC 750, but that's now getting phased out. They're no longer offering that. You have one right there? Yeah. Does up to 4 valves.
Mhm.
Yeah. And they're now coming out with these new controllers. They now require 120 volt valves. And they're changing the whole game of how things are done from an EMS standpoint. So now going back to my legend.
Was that a chicken?
Was that chicken?
I don't know. Your background looked like a chicken or a rooster.
No, my background is my wife and I in our wedding.
Oh, that was really quick. I didn't see it that fast.
We got married in We got married in a brewery. So if you look closely, you'll see it's all the cans that are all lined up next to us and behind us.
See, I thought this was the red part and that was white. Never mind. I saw it really quick and I was trying to catch what it was. Sorry.
All good. Okay. So if we look here at how we size the system, this is the low temp side of rack A.
Mhm.
You'll see that I only allowed for about 7.5% spare on the low temp. The reason for that is we're sharing some spare with the medium temp, believe it or not. Because if the medium temp compressors are oversized, they're going to do a lot of the work that the low temp doesn't need to do. So you don't need to go as wild with the low temp as you do with the medium temp, which you see here. I got 28.5% on a medium temp, or 20.05% on a medium temp.
So you're doing conventional booster. You're not doing parallel compression, right?
Correct. We actually looked at parallel compression. This project is in New Jersey. So we didn't end up needing parallel compression because the ambient conditions didn't require it.
Okay.
Parallel compression is good for situations where you need to bypass gas around the medium temp compressors to keep the operation of the system up and running. Parallel compression is good for high ambient conditions. Situations where you're going to run transcritical most of the time. Parallel compression helps keep you down in the subcritical range.
So the ROI for a place like New Jersey wouldn't be beneficial, but you put a rack like that down in like Houston, Texas, you need that parallel compression to save the energy consumption versus what it would cost the equipment, the VFD, the compressor. You know what I mean, right?
And really, Brett, that's really what it all comes down to when you're designing a CO2 system. What you're trying to do, and what we've been trying to do over these last couple installations that we've designed, we're trying to prove to these end users that yes, CO2 is the way to go as long as it's designed correctly. It'll be energy parity and possibly energy favorable to a DX system.
Mhm.
And we have to design it accordingly so that they can see the proof in the pudding once it gets installed.
Good.
Yeah. So that's where we stand right now. And then as far as the gas cooler is concerned, if you come over here, you can see that we still design it on a TD. We can see that this gas cooler has an operational capacity of 6,600 MVH
10-degree TD. Okay.
and 10-degree design TD with an actual TD of 7.82. So we're right around, what a DX system would get you.
Do you get more total heat rejection? I guess you wouldn't. You wouldn't get any more total heat rejection out of a CO2 booster system as what you typically would, because basically you have less compression ratios, which means less discharge superheat, correct?
Correct. Exactly.
Okay.
And you're circulating. You got to think about this. Your mass flow is drastically lowered from a DX system. So you're not passing as much gas around the system as you would with a DX system.
What were you gonna say, Kev? Oh, I thought you sorry.
And the more gas that you have to handle in a refrigeration system, the more load it incurs on the system.
Mhm.
When your refrigerant gets 3 times more BTUs per pound than a standard DX refrigerant, it's obviously going to be more efficient from a average standpoint, basically.
Gotcha.
So, and then yeah, like we were talking about before with the desuperheaters, we specified a small 1x2, just standard air cooled gas cooler
Mhm.
for the desuperheater, just to temper the low temp gas coming off of the compressors.
That's a pretty big desuperheater for weighing 532 pounds.
Yeah, well, it's only 1x2, but it's got a pretty good amount of capacity because it's kind of tall.
Gotcha.
Yeah. So yeah, then if I go into let's go into let me go into my calculations folder here. I'll open up some compressor calculations. So now as you can see here, we have a couple iterations of our rack selections.
Got
One with parallel compression here. I'll open that first so you can kind of get a look at that. Now you see this is the Bitzer, this is right on the Bitzer software.
Mhm.
Here's the diagrammatic of the system.
Okay.
Well, you have your low temp cases here, or low temp fixtures here. You got your low temp compressors over here. This is your desuperheater here. These are your medium temp fixtures here. And then these are your medium temp compressors here. This is your parallel compression right here.
Oh, so you ran it with that to see how much energy it would consume versus whatever in the high end or in the area that Jersey gets?
Yes, what I did was
Okay.
I looked at the COP of a system with parallel compression versus
Yeah.
a system without, and it actually worked out in favor of not having parallel compression.
That's so cool.
Yeah. Yeah.
I mean, I'm really lame, but that's so cool.
Yeah. And then they guide you through the whole selection process. You can actually, the Bitzer software is really neat because you can select any combination of compressors. You just tell how many compressors you want, and then you select how big how big you want them to be. In this specific situation, we didn't want 50 horse compressors across the board. So we went with more low temp compressors because they're easier to replace or easier to source and replace.
Oh, gotcha. Instead of
Yep.
having to get some big bastard.
Correct. Exactly. Exactly.
Okay.
Now, there is a company that's coming in the door from Italy. Their name is Doran Compressors. They're coming in hot and heavy in the United States right now, and they have a wonderful, wonderful offering for a compressor. They actually, yes. So actually, I'm not going to reveal any trade secrets, but the one big benefit I see is that they have a pocket inside of their compressor where all the discharge gas goes. It doesn't go into the main crankcase of the compressor. It's channeled into a separate cavity inside the compressor, and
Really?
it keeps the compressor cool.
Hmm.
It's very, very neat.
So that would be less total heat rejection then, right?
Less heat add into the system from the
Yeah.
compressor itself. Like you don't have to worry now about adding in the kW of the compressor into your heat load.
Oh shit, I didn't think about
Yep. Yep. Yeah, because we all know what the calculation for THR is, right?
See, I love talking to you because then it makes me realize how much I really don't know about anything.
The calculation for THR is quite simple if you know two things about your compressor. If you know the capacity of the compressor, and you know the kW consumption of the compressor,
Mhm.
it's basically capacity plus 3.413 times the
Mhm.
kW. That gives you your THR for the compressor.
Damn, you gotta write this. Okay.
And basically what you're doing is you're converting kW to MVH. That's it. And then adding the two together.
Oh, that's all you're doing. That's all you're doing.
It's all you're doing.
Yeah, I just Philip do it for me.
Hear that, Doreen? You need to get on it and get an app out so we have those calculations.
Actually, Doran does have an app, so I will.
Come on.
I'll send
Really?
you the link for it. Well done.
God, I hate you. There's all this stuff you have and you don't share.
Yes,
Maybe
I
in
do. I just don't share it until you ask for it.
Yeah, but I don't know I need it until you tell me it exists.
And that's why these conversations are good, right? So you'll see here one other thing that's different with a CO2 system that you're not going to see with a DX system. We like to size our compressors fairly evenly. Don't like uneven stepping, unlike supermarket designs where we like uneven stepping, because especially in this given instance, this is a large refrigerated warehouse. We're not going to have a lot of load variation, and we're not going to have a lot of steps in our capacity requirements. So we just size a bunch of compressors, all the same size, put a VFD on the lead, and off you go. Then you get
Cool.
zero. You get 0 to 100% modulation because you have all your compressor size the same with one VFD. Down, turn the compressor off, ramp back up, ramp down, turn the blah blah blah, go on and go. You can do it that way, basically. Yeah. So and now you can see that I'm riding the line here I'm riding the line of the application window for the medium temp compressors. But this is one thing that they show you in the Pitzer software that's really neat. It shows you where your condition lies in the operating envelope of the compressor you're choosing.
I lived on the wild side for that first one.
Yeah, well, I believe that's the parallel compression. So,
Okay.
so that's only needed in extreme situations, basically.
Gotcha.
And then they give you a little PT chart, kind of show you how the cycle works, basically.
So let me ask you a question because Jersey isn't not necessarily the most not humid place in the world. So
Sure.
I mean, why a Baddock over dry?
So, okay. So let me bring up my ashtray conditions from Jersey.
I'm sorry, because I'm wondering typically how much energy you really get out of an Baddock? Because I mean, that's why you're only getting a 10-degree TD rather than a 5?
It really depends on your ambient conditions. And here's the kicker. When you're sizing gas coolers, the decision to go from dry to adiabatic really depends on the differential between your wet bulb and your dry bulb. If your wet bulb is 10 degrees or more lower than your dry bulb, go adiabatic every time.
One more time. If say it again.
If your wet bulb, ambient wet bulb on your ashtray printout is more than 10 degrees less then the dry bulb. You go
Okay.
adiabatic every single time because you're going to get the bang for your bucket,
Gotcha.
right? Because you're able to lower that head pretty far, right?
Well, I've always been kicking this around, like the you save a little bit of energy in the head, but your water costs are through the roof.
It depends on what type. Okay. So I'll address that elephant in the room. Really depends on what brand, what manufacturer of adiabatic gas cooler you use. If you use a Baltimore air coil unit, the Trillium, that
Yeah,
recycles the water and only dumps once a day.
correct.
Gutner and Avapco, they fill and drain continuously. So then your water usage goes through the roof.
So yeah, I mean, like in places like Chicago, like I mean, we had a customer put a Gutner in,
Yep.
and it's using a massive amount of water. Well, they're getting a massive bill.
Well,
So
that might have to do with the fact there's onboard controls in that gas cooler, right?
yeah,
So it may be that piece of equipment never got commissioned properly, and it's just dumping. You know what I mean?
It's a high probability. Those things typically need to always be programmed. They send you
well,
that thing on the thumb drive and stuff.
they're programmed.
What's that?
They're programmed.
They are.
Are programmed. Okay. Okay. Well, I personally, I prefer the BAC unit to any other manufacturer because they recycle their water and they
Yeah,
only dump once every 24 hours.
they
Um,
they are they are a nice unit.
yeah, and they have the pads readily available for replacement if necessary. They have the EVM PAPS motors readily available if you need to replace them. You're not a manufacturer that's not supporting their product. You know what I mean?
So check this out. When we were down in the HR, we had a conversation. There was a over in, I don't know if it was in Europe, but some places are actually starting to take their condensate water out of their cases
Yep.
because the solids are basically going to drop out. You know what I
Yep.
mean? So they have to briefly filter that water.
Mhm.
They you then use that water to refill that,
That's a smart idea.
right?
That's a really smart idea.
Think about it, because it's
Yeah.
already going to be filtered. All the shit's going to fall out of it, and now you have nice cold water that you can basically just put in that adiabatic. So how much more extra capacity? It's really hot out. We'll just let that water just pump up there.
Sure. Sure.
Like places like California where they're like dictators with the water. I mean, that would be like perfect. That particular stuff was in South Africa. He was telling us that, Brett.
No, is that where it was? Okay, I could
Yeah.
remember. He does stuff all over the place. So I could remember where the hell it was. We talked about so much shit.
Oh, close my door.
The loudest door ever.
Not true that door you have that you need to oil the hinges every time your kids open it. It sounds like a creaky old man.
Nice.
All right. So now we've gone through compressor sizing. We've kind of gone through the idea of adiabatic gas coolers versus dry.
Mm-hmm.
We haven't really gone through here. I want to take you through. Let me start up another session of my work. Then I'll take you over to the Baltimore Air Coil site and I'll kind of show you how they help us with gas cooler selections.
Oh look, I know that site.
Yeah.